Built like Friday. Yeah, I'm like, oh, that's tomorrow. And I was like, what
I thought it was like last Thursday.
Okay, so we're gonna start with talking about. I feel like we should skip 33 and 34, not like skip them, but those are identical to the collision questions. And Lindsay, could you put your computer away, please? Thank you. If you get stuck, so you treat them exactly like the other questions. You take the how much total momentum does the system have after the push, right? That push is like an internal force that is going to preserve the overall momentum of the system. So the analysis of 33 and 34 is identical to the collision questions. It's just the context is slightly different. But I do want to look at 35 though. It's I briefly mentioned this in class the other day, which is like this is kind of one of the principles behind which like a rocket works in space. By the way, NASA's landing this new rover on Mars.
Perseverance.
Huh?
Perseverance.
Perseverance, exactly. It has a little drone named this little helicopter's name. Forget.
Strawberry frosting and like sprinkles on it, so it looks like.
Huh?
No.
Of course,
Phil.
you're
It was on like 2 radio stations in the news last night.
What was?
The Mars donut from Krispy Kreme that's like limited edition today. It's a chocolate filled donut.
Caleb knows all the
Strawberry
details.
frosting and sprinkles on it, and it resembles Mars.
Hence the name Mars
And it's only
Donut.
available today.
Wow. That's from Dunkin' Donuts? No, that's from. So you got a Dunkin' Donuts for the Charlie D'Amelio caramel frappalock to that Lapatapo. And then you go get the Mars donut. Okay. So this spaceship has a mass of 700 kilograms. Okay. With its fuel, it's a total mass of 700 kilograms. So let's maybe represent the fuel with like a little shaded rectangle there. And basically, the spaceship is going through space at 20 meters per second. So this is sort of the before picture. This is before. So now a quick little review of Newtonian mechanics here. Is there any force required for this thing to just be moving through space at constant speed? No. Okay. Net force is 0. I mean, there are no forces acting on this, assuming it's out in deep outer space. Okay, no forces. But after a chemical reaction takes place, combustion, this is ignited, and it is basically ejected backward. So this fuel. So now this is empty, and now it'd probably be in the form of some kind of gas, but you know the way. That's a nice gas cloud there. What's the mass of that gas cloud? 50 kilograms. Okay. It's a big thing in chemistry, right? Conservation of mass. If you're taking chemistry, if this substance turned into a gas, it's still the same amount of protons and neutrons, right? It's still the same number of atomic nuclei, so the mass isn't changing. Unless some mass is lost out of the system. But in this case, our closed system is like this. So here's my system, okay? The mass is still in that system. So anyway, so now that gas cloud is traveling backward at 800 meters per second. That's pretty fast, right? And the question is, well, how fast is the ship going then, if that happened? So what's the mass of the ship? 650, very good. Okay. So that's the key there. If you call that 700, the math is going to work out to give you some nonsensical answer. So the key is that it's losing that mass. So it's transferring some of its matter backward, and so the momentum of this guy, the velocity will increase to conserve the momentum. Okay, so do the calculation. I gotta get a new marker. Do the calculation and see what you get. Compare answers.
So you set it up on calculator. What are we supposed to do?
Population, Joe.
No, I
So,
No, I wasn't.
it's going.
He was saying about Mars, but
Hour.
I was.
Did you be here for a second?
I'm gonna, I didn't make a trip.
Well, I can check myself, get a box.
If I get one and then I keep it.
Sell it like 30 years later.
I'll preserve my Mars stone for eternity.
I mean, could you really
And
go?
I'll put it on my deathbed.
But it could be really bad. I'll put you over That'll finish the job.
That's why I want to go out eating my Mars stone. Think about it.
I'm the first man wearing one.
Yes.
Okay, so there's the setup of it, right? Keep going if you're still working, get the answer. But that's just, the setup is just the total momentum of the system before
Yeah.
must be equal to the total momentum of the system after. So if you understand that concept, that momentum is conserved, and you know the formula for momentum, then you're all good to go. You're all set.
One down, three.
You do that by 1/2.
So this is.
Do, do, do. Okay, so that's the critical step there. From there, the algebra should be relatively straightforward. But you may have, you don't have to say it, but then you guys maybe forget to make the 800 negative. That's probably the most common mistake here. If you forgot to make the 800 negative, then you got some weird negative number that might not have made a whole lot of sense. So anyway, let's solve this. Who got an answer? What's the answer? No one?
I'm almost.
83? Sounds reasonable. So I mean, yeah, so 14,000, add
I got
40,000.
somebody said 83. Right?
So you can see that this can, if you look at the size of these numbers, 14,000 and 40,000, this contributed a whole lot. This has a big effect on it. Right? This number is big compared to this number. So then divide that by 650, and yeah, I got about 83.1. I agree with Emily. So so if you look at the numbers here, I mean, the bigger this number is, right, the bigger this number will be. Right? Does that make sense? So which means, yeah, the faster you can eject that fuel, the more speed you're going to impart to the ship. Likewise, if that number is bigger, then that'll make this number bigger, which just means if you have more fuel on board, you can get more momentum. So, okay. And also just keep in mind, you don't necessarily have to ignite it. I know there's some, don't they have little astronaut suits have little like compressed air canisters that can just shoot little jets out. So you just have a compressed gas that's at pressure. Well, the pressure around it's zero, vacuum of space. That gas really wants to escape the canister. So what'll happen is, here's the astronaut. This is gonna be Emily in a few years. Space helmet. There you go. There's like a little jet somewhere on, like, say, on the shoulder. It's a little canister. So all these gas particles are trapped inside. They're going bing, 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 bing around inside the canister. That's called pressure. So anyway, when you release the canister, these gas particles want to escape, and so every particle that escapes with speed is going to have an effect of actually like basically pushing the astronaut the other direction. So they can kind of adjust their position and speed and stuff. That's pretty neato. Anyone else want to be an astronaut? That'd be a pretty lit job.
Cool.
Yeah, cool.
Like I'm not like technically like pursuing astronaut. Like I just want to fly. Then like if I get to the level where
Something I
I could
like
be an
to know, but if
astronaut.
somebody was like, hey, you
That's
want
like
to
a
go to space and go to Mars, I'd be like, hell yeah.
Would you go to Mars if they were like mission to Mars and they would go, Bailey, we've picked you out of this. You're the perfect specimen to go to Mars and be part of the first human colony on Mars, but you're never coming back to Earth. You're gonna eventually die there. Would you go?
Emily, are you in this game?
I think I'd go.
Okay.
SpaceX.
Mars Donuts and I'm going.
SpaceX.
I think it's an interesting question. Would you be part of the first human colony? Let's say it's 1,000 people. They're going to send 1,000 humans to Mars to start a colony, do research, send data back to Earth. But there's no chance that you're ever going to come back to Earth because they're not going to have most likely they're not going to have the equipment to send a rocket off of Mars back to Earth anyway. So is that would you say that's correct? Is that right now the plan would be anyone that
Yeah,
at first.
they don't have enough fuel to get them back.
The SpaceX recently did a thing where you could like enter to win a lottery to go on a Falcon 9 rocket to space and just like orbit Earth. I was trying to sign up for it, but you have to be 18.
I'll sign up for it.
That'd be a little scary. You know what's funny? If you'd asked me when I was your guys' age, I would have jumped on. I would be like, yeah, I'll go to Mars. But now that I'm getting older, I'm like, no, I guess I would.
You gotta.
Paigey, I need Paigey.
Take her to Mars with
If she wanted, if she really wanted to go, I guess I'd go.
And you leave us behind to try to figure out physics
Yeah,
ourselves.
peace out.
I'll take your Steve.
Okay. So yeah, I'll leave my ski stuff to you.
You can ski on the Beverly Hills of Mars.
That's true.
Oh, you could
That's
see
true.
the poles up there.
There you go.
There you go. Fresh powder for days.
You could talk something.
Isn't that like one of the tallest mountains in the
It is.
Olympus Mons,
Yeah.
right?
Yeah.
There's
Then
not
you
snow on
could
that one,
sneeze on everyone, and be like, "Oh, you climbed Everest? Oh, that's pretty funny. I climbed the Olympus Mons."
though. With a spacesuit on.
What's the elevation of that?
Well, there isn't really a sea level, I guess.
60,000? Or I don't
Isn't it
remember.
like so big that you don't really notice you're even on a mountain that?
Yeah,
Yeah.
72,000 feet. It says.
Oh, I nailed that.
What would happen?
And Everest is like 29 something,
Yeah.
so it's over twice as tall. Yeah, that'd be a good flex.
That would be a
Flex.
flex.
Good flex of
Just a
that.
flex on, you know. How would it climb a mountain? Anyway, but yeah, Zach, I think that's right. It's so big that you can't even really see it apparently, from what I've heard. But,
Have you seen what they're talking about with like the new rovers and stuff that they're going to have like drones on them?
You'd be sick.
Yeah, the new one has
to
a
fly to different places.
Yeah, the new one. I'm looking it up. It's Perseverance and the robot
Bill.
Phil.
Isn't it actually? Oh.
No, the rover is called Perseverance, and then the little drone is named. Where is it?
Perseverance Junior.
No, it's. Although, hey, Julia, Perseverance's nickname is Percy. There you go.
Okay.
Ingenuity is the helicopter. Did you get it?
Yes.
I didn't hear what you said.
Oh, that's right. Yeah, it's cool.
Ingenuity.
What's that one's nickname?
Okay, looking for like.
What's
Jenny.
Ingenuity's
I'd call it
nickname?
Jenny.
Mr. Halls like the golden on like capes. Like
I don't know much about
They have
it.
so many.
I'm trying to remember if this is the one where you could have put your name on the thing. My wife actually did that. She submitted her name into this thing where then they like use an electron. It's like electron etching technology to like etch it was like 100,000 names into this little tiny silicon chip. Anyway, so she did
Was that the one that's going to Mars?
I think it's the current one.
She can get a free donut at She brings food.
Oh, if your name's on it?
Yeah.
Krispy Kreme. All right, guys, we're gonna do
Probably
36.
rolling out after school.
So 36.
Are you like an ambassador of Krispy Kreme or something? Or like, I just really want to try a
They
donut.
bought enough donuts that
I
you have stock.
So 36, you might go, well, this is like the same thing as the questions we've done before. It pretty much is. There's just like a little bit of a twist to this one. So let's do 36. Like, you got block A is 20 kilograms, and it's going 10 meters per second, and block B is at rest. So block B is 4 kilograms. So just intuitively, you could probably just figure out, I mean, this guy's 5 times heavier than this guy, so he's gonna kind of just plow right through, right? So he's gonna, and it says after the collision, block A is going 7 meters per second. So here's our 4, and then after the collision, they bonked into each other. It says block A is traveling to the right at 7 meters per second. And we're going to figure out how fast is block B. We don't know the answer. But logically, it has to be going to the right. We know that for a fact. Okay, okay, go ahead and calculate V. And how about this? Try your best to just answer all these questions. I think the only thing that's even slightly new is now I'm asking you stuff like, what was the force experienced and what was the accelerations? Now, how do you get that? Well, you might go, well, I need some time values for that. Well, there you go. The event of them colliding took 120 milliseconds. So anyway, try your best on that, and we'll check answers in 5 minutes. A quick little check here. You should have got, was that 15?
Yeah.
Okay. If you didn't get 15, you're probably lost. I can come talk to you and help you out. I'm just trying to give you a heads up. Like that should be hopefully fairly straightforward by now. If not, I'll help you get it sorted out as best I can. But just go mass times velocity, that's mass times velocity, set it equal to the mass times velocity, that's mass times velocity, do the algebra. Then for B, go ahead and get an answer for that. You're going to want to separately look at like what happened to block A, what happened to block B. What was the change in momentum? Did you get it? Keep going. Move on to. For C and D, I mean, depending on how you want to think about this, you might do D first. You might calculate the acceleration because you know the velocity change for each block and you know the time that it took. That's an option.
I'm going back to do each picture.
Which is negatives. Okay. Did we get anything? Hopefully, look at these answers you're getting and go, maybe there's some sort of message here. What was block A's change in momentum?
-60.
Yeah, so the change in momentum for A, you got 60. So it would have been, his initial momentum was 200, and his final momentum was 140. So you do something like 140 minus 200. Is everyone okay with that? So that's a final answer. I should put units on it. Kilogram meters per second. The change in momentum for block B, his final momentum was 4 times 15, which is 60. And his initial momentum was 0, so he has positive 60 kilogram meter per second. So now think about that. Is that a coincidence?
No, because it's conservation.
Yeah, conserve momentum. So how much does the total momentum of the system change? 0, nothing. So whatever momentum A loses, B must pick up. Okay, so this is a universal thing. This is going to always be the case. Two things collide. One thing is going to gain some momentum, one thing's going to lose some momentum, but the total change of momentum has to be 0. If it's not, then momentum wasn't conserved. So then, how about for part C? What did you guys get for C? The force experienced. Or did anyone do D first? Anyone do D first? Okay, did anyone do C first? How could you do C first? Think about that. Is there a formula that relates a change in momentum to time, right, and force?
Oh. Yeah.
Remember the impulse equation? Change in momentum is equal to the net force times time. Remember that? It's a pretty important equation to think about. Oh, I don't know. That's certainly not as fundamental as like the definition of acceleration. The definition of acceleration is by far a bigger, more important thing to know. So let's do it that way. Acceleration would have been, so for block A, the acceleration would have been the change in velocity over how much time took place. So what was A's change in velocity? -3. Very good. Everyone okay with that? He went from 10 to 7. And how much time took place? It's given in the problem.
120 milliseconds.
120 milliseconds. So you need like a high-speed camera or some kind of instrument to detect that. How long were these things actually touching for? So 120 thousandths of a second, what does that come out to be? Negative,
25.
25 units meters per second squared. Everyone okay with that calculation? Okay, let's look at it for B. His acceleration is change in velocity over time. Block B went from 0 meters per second up to 15 meters per second. So 15 is this change in V. What do we get there?
125.
125. Okay. Does any brave soul want to comment on the relationship between those two numbers? Julia.
Oh, the mass of block B is a fifth of the mass of block A, and the acceleration of block A is a fifth of the acceleration of block B.
Boopity boppity. Gail, yes, you got it. Okay, so good. So then what does that maybe mean for C? Start thinking about C. Well, how about the forces involved? You might have answered C, at least not numerically, but qualitatively, like, well, Newton's third law, every force has an equal and opposite force, right? And when I push on the wall pushes back on me, kind of thing. So the blocks logically must exert the same force on each other, right? If not, that's like, excuse me, Newton's third law. What up? What's going on? So let's see, does the calculation make sense with these numbers? Yeah, because F equals ma, right? Force is mass times acceleration. Or maybe you figured it out using this one. It doesn't really matter. That's kind of the beauty of physics, I think, that it all fits together. It's this really nice system of describing things where everything just kind of fits very, very nicely and logically together. So anyway, let's do for block A, the force experience would be his mass, 20, times his acceleration, negative 25. So block A experienced a force of negative 500 newtons. Does it make sense why it's a negative number? Yeah, because block B was pushing backward to the left on block A when they hit, right? How about for block B? His force is mass times acceleration. His mass is 4, and his acceleration was a positive 125. That gets us positive 500 newtons. So Newton's third law, obviously is going to agree with all this stuff. So when block A pushes on B, B pushes back on A. Yes?
Okay, so the question I have, like in the original formula, we had that change in momentum equals force times distance, or force times time. Why don't we actually multiply bottom one, like in the one that we just did? Why don't we have to multiply by time? Is that because we already calculated time in D?
Yeah, so we did D first and just calculated what's the accelerations, and we know that force is mass times acceleration. This equation up here is equivalent to this equation. If you go back and look at how we got this equation, we started off with this and then just used the definition of P equals mv to get this. So we could have gone straight to C and said, well, look at these blocks. Like look at block A, for example. How much time did block A experience the force for? 0.12 seconds. What was the change in momentum for block A? Well, negative 60. If you go negative 60 divided by 0.12, you're gonna get that number. Divided by, negative 60 divided by 0.12 would give you a negative. And the same thing. So for block B, you'd be like, well, block B has the same force and the same amount of time. No, sorry, the same force and the same change in momentum. Did I say that wrong? No. Yeah. Same force logically, same time, same change in momentum. So it's all gonna work the same. Okay. Are there any questions? Yeah. Sure. Is this easy peasy or? Okay. And then, did anyone determine the elasticity yet?
Inelastic.
It's inelastic?
Well, if we're still going off the previous, like, it's not.
Is it close to being elastic?
Well, it's 1,940, so it's pretty
Oh.
close.
Oh, yeah, that's, yeah. Yeah, I would still say technically that's inelastic. I mean, so, yeah, for elasticity, you just calculate. So you say, what was the initial energy of the system? Okay, you go 1/2 mv squared plus 1/2 mv squared, which gets you 1,000 joules. Okay, so the system before the collision had 1,000 joules of energy. All the energy was just stored in the movement of the mass, kinetic energy. The final energy of the system would be 1/2 mv squared plus 1/2 mv squared. And you said that comes out to what, Aaron?
940.
Okay, you guys all corroborate that?
Yeah.
Okay,
That's what I did.
so this is, I would say, it's not a super inelastic collision, but it is inelastic. We can say it's not perfectly elastic at least. It's inelastic because 60 joules was lost in the form of heat, sound. Okay. All right. Last thing to just talk about really briefly is 37 doesn't give you much information. It just says if a 5 kilogram block collides with a 10 kilogram block. So think about the results on 36. Okay. If a 5 kilogram block and a 10 kilogram block collide, who will experience a greater acceleration? Or will they be the same?
Unless,
I mean,
unless the 10 is at rest and the 5 will.
I know it's tempting to think about their speeds, but think about, maybe let's start with B. If two things run into each other, what's true about the forces experienced by those objects?
They'll counteract.
They're equal and opposite. Newton's third law, right? So these guys, so the answer to B would have to be, it must be, unless Newton's wrong, which he's not, okay, is that A and B are the two blocks experience equal and opposite forces. So those forces have the same magnitude. Okay, does that make sense?
Yeah.
So there's a couple things going on here, guys. So this question really is just asking us to look at like what during this collision, a collision takes time, right? Every event takes some amount of time to take place. So the change in momentum is going to be the force times the time, and also the force is equal to the mass times the acceleration. So Newton's third law tells us that they're going to have the same force. Okay, so if they have the same force, but one of the blocks has a bigger mass, what does that mean for its acceleration?
it has a smaller
It's
acceleration.
going to have a smaller acceleration. Okay, does that make sense?
Yeah.
Okay. Now, when two things collide, if you ask them how long did that collision take, are they going to give you different answers? No. They both experience the same event, right? So they're experiencing the same force for the same period of time. So what's going to be true about their change in momentum? It's
Same.
the same,
Yeah.
or equal and opposite, if we want to be more precise, right? If the 10 kilogram block gains this much momentum, the 5 kilogram block will lose that same amount of momentum. So in terms of magnitude, they will Am I like belaboring the point here? Do you guys get it?
Yeah, we get it. I'm trying.
So just to clarify, the answer to A is who experiences the greater acceleration?
Kilogram block.
The 5 kilogram block. Who experiences a greater force?
Equal and
They're
opposite
same,
forces.
samesies, equal and opposite. How about C? Equal and opposite. Okay.